Hi there. In this video, we're going to talk about double integrals. A double integral is the way we integrate a function of two variables over a region in two dimensions. So let's take a look at what we have here. I have a graph of a function of two variables. Right, there it is. And I want to compute the integral over a region. So I have the region depicted on the left here. Let me blow it up for us. All right, there it is. It's the region. Now the fonts are very small. I apologize for that. I can't really fix that. The region goes from x equals -1 to 1 and y equals 0 to 2. So this is a rectangular region. In fact, this one is a square. So we want to find the integral over this region, right? Now remember what this is in single variable calculus. If we do an integral over an interval, we are finding the area between the graph and that interval. Now, technically, we should be a little bit careful about how we say this. I like to call it the signed area because the parts of the area that dip below the x-axis are negative, whereas the parts that are above the x-axis are positive in that case. So it's really an area that can be negative or even come to 0 if the positives cancel out the negatives, right? So in this situation, we are finding the volume, the signed volume between the graph and this region. Let's put this region in to the three-dimensional picture here. And where are you, region? There you are. Okay, so there's the region. We are integrating over this region. So we want to find the volume between the graph and this region. Let me go ahead and put what that volume would look like. That would be this object here. So we want to find the volume of that chunk, that colored chunk, right? That's what we want to find the volume of. Now remember how an integral works. An integral is defined by splitting the region or the interval in single variable calculus into little bits. And you can see that that's kind of already been done for us. You can see the region has been split up into little squares, right? And then above or below each square, we're going to have this chunk, right? This little volume. So what we're going to do in the integral is we're going to approximate this volume using the height of the graph. And we're going to do that for each one of these little pieces. And we're going to add up all those little volumes. And that will be an approximation for the integral, the answer that we want. Now, we want an exact answer. We don't want just an approximation. So what we're going to do is we're going to take the limit as the size of these little chunks goes to 0. So we're going to make these squares that you see here smaller and smaller and smaller, and they'll have to become more and more numerous to fill this up. And because we're using finer and finer instruments to make our approximation is going to get better and better and better. And when we take the limit, it will approach the signed volume between the region and the graph. And that is how we define the double integral. All right, so this is the integral that we were just looking at, the double integral. We want to compute the double integral over the region R of this function. Okay, so what is R? Well, R is the set, this is the notation for set, of points, x, y, such that x is between -1 and 1 and y is between 0 and 2. Okay, so that describes this rectangle down here. Now, we also have some other notation here. So actually, first of all, notice that I put the region that I'm integrating over below the integral signs. Okay, I'd write it below that, and then I can describe that region down below. Right? Now, to the right, I have a dA. Now, you might be used to, from single variable calculus, seeing on the right a dx or a dy. Well, if we have a dx, that's because we're integrating with respect to an infinitesimal change in x. Right? We're segmenting the x-axis, we're partitioning it into little pieces, and we're finding the infinitesimal area above or below those pieces. Well, here, instead of just going along the x-axis, we're actually finding infinitesimal areas, as I described in the previous video. So we have dA. And let's just draw a picture of what's going on here. So to approximate the volume, what I do is I segment this this region into small bits. Okay, so we're going to just segment it down into small little rectangles. Now, each one of these rectangles has a width and a height. The width we're going to call delta x, and the height we're going to call delta y. Now, that little rectangle has an area. Okay, that area is going to be denoted by delta A. But because it's a rectangle, delta A is equal to delta x times delta y. Now, what we want to do is we want to find the volume. We want to approximate the volume between the graph of the function and this rectangle. So what we're going to do is we're going to take any point in here, and we are going to find the height of the function. If we multiply the height of the function times the area of this rectangle, we will get the volume of a box sitting above this rectangle that goes up to the height of the graph. And that will approximate, won't be exactly equal to probably, but it'll approximate the volume under the graph. So the volume is going to be the height of the function multiplied by delta A. That will give me the volume of, so if my box was down here, this is my dx and that's my dy. I'm drawing it in 3 dimensions there. I go up to the graph and I get a box, right? So it's the volume of this box. And the height here, as we said, was the height of the graph. Okay, so that's just the volume above one little piece. Now I want to find the total volume above the entire region. Okay, so how do we do that? Well, let's write that down below. The total volume is going to be approximately equal to what we get if we add up all these approximate volumes. Okay, so I'm going to add up. So suppose there are n of them. Just count 1, 2, 3, 4, 5, 6, 7. We have n of them, all right? And I'm going to add up these little volumes. Okay, so I'm going to add up these. So that's the total volume is approximately that. Now, how can I get the actual volume instead of just an approximation? Well, what I'm going to do is I'm going to take the limit as the size of these little approximating pieces goes to 0. As the size of the pieces goes to 0, the approximation is going to get better and better. And in the limit, as the size of the pieces goes to 0, and consequently the number of pieces goes to infinity, because you need more and more of them to fill this space up, the approximation will approach the actual volume, the actual total volume. So the actual total volume will equal the limit as n goes to infinity, as the number of pieces goes to infinity, so the size goes to 0, of what we just wrote down there. Now you should recognize this from single variable calculus. When you take a sum of things like this, in the single variable calculus we had a delta x here, and so this was a little infinitesimal area. We added them up and took the number of them going to infinity. This is the definition of an integral. Well, in multivariable calculus, we're doing it with respect to area, so instead of writing a single integral sign, this is what this means. And so we'll write f of x, y, and to denote the fact that we took a limit and that this quantity, delta A, actually went to 0 in the limit, but to remind ourselves that it was there, we write a dA. So sometimes people think of dA as an infinitesimally small area. It's what this kind of became as it went to 0 in the limit. All right, so we just use this as a reminder of what was once there. All right, so that's what this notation means. It means to do this approximation business and take the limit as the approximation gets better and better so that we get an actual exact answer. Okay, so now before we actually go and compute the integral, we need to point out one more thing that's very important. Okay, and it's called Fubini's theorem. Okay, let's take a look. So Fubini's theorem, which needs to be centered on my screen. Come on, Fubini. There you go. Okay. Okay, Fubini's theorem tells us how we can break up this double integral into simpler pieces. Okay, so it says that if you have a function that's of two variables that's continuous over a rectangular region, all right, just like the one we had, then the double integral is equal to what is called an iterated integral. All right, so we have this double integral. This is the thing we started with. All right, now we can split this up. Now remember I said that dA is the same as, so delta A is the same as delta x times delta y. Well, that means that we can write dA as dx times dy. All right. Well, what we can do now is what Fubini's theorem is telling us is that we can split this up into two other types of integrals. And these are called iterated integrals. This first one, if you just ignore the dx for a moment and look at this, this is an integral of one variable. So we're just integrating a function, treating x as constant and integrating with respect to y. Okay? Now that will integrate out the y's and leave us with a function of x. So now y is gone and we only have x, which we can then integrate with respect to x as another single variable calculus integral. So we're doing two single variable calculus integrals, one after the other, and that Fubini's theorem is telling us that that will give us the double integral. And Fubini's theorem says that we can do it the other way around too. Instead of doing the y first and then the x, we could do the x first and then the y. So we would first treat y as a constant and integrate this with respect to x. That would integrate out the x's. Now only y is left. So this is a function of y, which I can now integrate with respect to y and get a value out. All right? So this is what Fubini's theorem is telling us, which is a great theorem. It's saying that we can split it up like this, and we can split it up either way. Okay, so one more thing. I just want to show you what's going on here when we split it up like that. So if you do the integral with respect to, let's say this is the y direction going this way, and this direction is the x direction, okay? So if I integrate with respect to y first, then I'm finding the area underneath. This is like a single variable integral. It's like the area under a curve. See that? So I'm finding this region, the area of this region. That's when I'm done with that first integral. So that was like doing this integral. I found the area of that little slice. And now what I'm going to do to get the volume is I'm going to integrate the area of those slices with respect to x. All right, so then I'm going to integrate in this direction. Right? And when I imagine this area, streaming across here and filling up this whole volume, then I'll get the entire volume. Right? That's what Fubini's theorem is letting us do. All right, so let's compute our integral. So the first thing we're going to do is we're going to use Fubini's theorem, which lets us split this double integral up as an iterated integral. Now when we do that, we saw we could do it dx dy or dy dx. In this case, it's not going to matter. Sometimes one might be a little bit easier than the other one, so you might want to think about it. I think this one doesn't matter too much. So let's just make it dx dy, okay? So we're going to do our integral dx dy. Now that means that the inner integral is with respect to x, all right? So x goes from -1 to 1, so that's these bounds over here. That's the x integral. Now the outer integral, we're going to integrate through all the x's, so the x's will be gone in the inner integral. And so for the outer integral, it'll just be a function of y, and so we're going to go from 0 to 2. So make sure you keep those bounds straight. Don't get those mixed up. Okay? So what we need to do is we're going to do this inner integral. Now that means we're going to treat y as a constant, and we're just going to integrate with this with respect to x. So if y is a constant, I can just kind of ignore that y squared temporarily. I can just leave it on the outside. So I'm really just integrating, just focus on this, right? And I think you can see that this just becomes this, all right? Now let me be clear. These, just to be extra clear, these are values of x. So we're evaluating this from x equals -1 to x equals 1. Okay, so let's go ahead and do that evaluation. Okay, so when I plug 1 in for x, I get and when I plug in -1 for x, I get okay, now we can simplify this a little bit. Okay, so that's what our integral becomes. Now, notice that all the x's got integrated away. We integrated with respect to x, so there are no x's left. If you had x's left, then you did something wrong. You probably forgot to evaluate one of them. Okay, so next step, we do this single variable calculus integral, and we anti-differentiate with respect to y, and we evaluate from 0 to 2. Which gives us our final answer, -16/9. Now let's just look back at the picture and make sure that this makes sense. Okay, there we had our picture, and if you look at that region up here, you can see, as we said before, it is below the xy plane, and so we should be getting a negative answer, so that makes me happy. That makes me think, okay, well, at least the sign is right, all right? So we're on the right track there. Always go look back at your region and just make sure, hey, this is looking reasonably okay, all right? So that is double integrals.